Hi, everyone. So now we need to talk about the three graphs that are on the second half of that document, the quadratic forms document. We did concavity at the top, and now there was three graphs. And at this point, my hope is that you've already graphed all three of them, and you've written down their key points, their vertex, x-intercept, and vertical intercept. And now we're just going to kind of summarize what you saw, do some vocabulary, and talk about the connections between the forms. So I'm going to share my screen with you. Hopefully this works. Bear with me here. And we will look at the Desmos graphs. Share screen. Okay, so you should hopefully be able to see my screen now. So what I have is I've already pulled up all three functions here on my Desmos. And what you should have seen, giant surprise, is that all three graphs actually were the same. They were the exact same parabola. The very first one, let me turn off my other colors here. So check it out. See that green one? That's this top formula right there. And then if I turn that one off and turn on the purple one, yep, same graph. And if I turn off the purple one and turn on the orange one, that's the one at the very bottom of your worksheet, graph number 3, they're all the same. So all three graphs ended up being completely identical. So definitely that was on purpose. Obviously, I knew that was going to happen. But what I'm trying to get at here is that we actually have three different primary ways that we can write a quadratic function. So this is now on the back side of your document. We have some vocab. So standard form, probably the most common form, is the way that number 1 was written. And that simply is y equals, or f of x equals, ax squared plus bx plus c. So that form is probably the most common, and it is called standard form. And it has the what we call A's, B's, and C's of the parabola. Now, you'll notice with regards to what information standard form is useful for, it's pretty much only the vertical intercept. So you see in the formula, the A value is 1.5. Okay, look at all those critical points. Are any of them 1.5? Like, no, not really, not at all. Then there's a positive 3 in the middle. Are any of the points positive 3? No, not really. And then you see the negative 4.5 on the end. And sure enough, the vertical intercept is indeed at negative 4.5. Now, just to make sure we feel good about that and that it's not a coincidence, if I actually plug 0 in to number 1's formula, you'll see that it's always, always, always going to be that C value, because check it out. If I do 1.5, but then I plug in 0, plug in 0 squared, plus my B value is 3 times 0. And then my C value, of course, was minus 4.5. So if you think about the algebra that's happening here, 0 squared is just 0, and 0 times 1.5 is still 0. The entire first term gets zeroed out. The middle term is 3 times 0. And again, 0 times anything is just 0. So your A term and your B term are always going to get zeroed out, but the minus 4.5 is definitely still there. So that's just confirmation that the C value is indeed always going to be your vertical intercept. But as far as any other key points, there's really nothing else you get out of standard form other than the vertical intercept. And also, I suppose we can't forget the little fun fact that if your A value is positive, that is what makes the graph concave up. Remember, if your A value is positive, it's right side up. If it's negative, it gets reflected. We saw that in our transformations activity. So since it's a positive A value, we know it's right side up. We know the vertical intercept is negative 4.5, but that's pretty much it with regards to what standard form tells us. Now the other one, number 2, that one's called factored form. And factored form looks like this in its most generic form. You've got A still, and then you've got these 2 parentheses. And we typically say that it's x minus, and then we subscript it as x1, and then times x minus, and then we subscript it as x2. That is factored form. And if you think about what factored form is useful for, so going back to our ordered pairs here, if you think about what factored form is useful for, you'll see that factored form is very much related to the x-intercepts. So if you look at the formula for number 2, in the parentheses, it said x minus 1. And notice one of the 0 points was at positive 1. And then the other parentheses in number 2's formula said x plus 3. And you'll notice that one of the x-intercepts was at negative 3. So they seem to be at the opposite, if you will, location. And that is definitely true. So I'm going to try to switch my screen here so that I can show you a little bit more detail. So stop screen, and then go back here. Is that my face again? And then share content, whiteboard. Okay, hopefully this worked. So if you think about that formula, so 1.5 and then x minus 1 times x plus 3. Okay, so why is it that factored form helps us find the x-intercepts? Well, the reason is because if you think about by definition of an x-intercept, you're wanting to know when the output is 0. That is what an x-intercept is all about, is that it's on the x-axis, aka the output value is 0. So if you think about what factored form says, it says that this thing times that thing has to be 0. In an x-intercept context, it would have to be 0. Well, think about it. Anything times anything will only equal 0 if one of these is indeed a 0 itself. 0 times anything is 0. That is the only way mathematically for the answer to become 0. So when you're trying to solve an equation like that in factored form, that's exactly why the answer to this is whatever value makes those parentheses 0. That's why the answer is positive 1. Even though the parenthesis says minus 1, the x-intercept is at positive 1. And then same thing over here. Whatever makes x plus 3 equal to 0, that's going to be your answer. Happens to be at negative 3. If you plug 1 in right there, 1 minus 1 is 0, poof, the whole answer is 0. If you plug negative 3 in right there, negative 3 plus 3 is 0, poof, the whole answer is going to be 0. So factored form is really, really, really helpful if you're wanting to know the x-intercepts. Does factored form help you find the vertex? Well, not directly, no. Does factored form help you find the vertical intercept? No, not directly. We'll come back and talk about that a little bit more in a minute. But for now, the benefits of factored form are finding the x-intercepts, period. Okay, so let me share, or go back, I should say, and try to, oh boy, there's my button that I want. Is it up here? I confused it. There we go. Stop share. Oh goodness, there's my face. Okay, so let me go back and share my screen, hopefully. Okay. And oops. Back to Desmos. Okay, awesome. So here we are, we're back. And then the last one is called vertex or translation form. So in terms of what vertex or translation form looks like, it's y equals, always starts with your a value. But then vertex form looks like this. It's, oops, parentheses, x minus, they typically use the letter h in textbooks. Why? I have no idea. Squared plus, and then they typically use the letter k in textbooks. Why? I have no idea. So vertex or translation form is y equals a times the quantity x minus h squared plus k. And if you go back and think about those critical points, does vertex form or translation form help you find any key points? Does it help you find the x-intercept at negative 3? Let's go back to my formula. What was my formula? it was 1.5 times x plus 1 quantity squared take away 6. So in any of those numbers, would you have had a clue that the x-intercepts were going to be at -3 and 1? No, probably not. If you look at that formula for number 3, would you have any clue that the vertical intercept was going to be at -4.5? No, probably not really. If you look at that formula and look at the vertex being at -1, -6, well, okay. So here's the -6, right? That's definitely there. But the 1 seems to be a little bit off, right? Because the parentheses say x plus 1. And yet, for some reason, the vertex is at -1. Well, ladies and gentlemen, that should actually come at no surprise. We just finished our translations unit, and if you recall, whatever is inside the parentheses is your horizontal shift. And your horizontal shift is in the opposite direction. So if it says x plus 1, yeah, it's going to go to the left 1. And then the -6, of course, that's your vertical shift. And that's just as is. So if it says -6, yeah, it's going to go down 6. So translation form is pretty much identical to what we just covered in our last unit, and that is translations. In translations, we used the letters C and D. Do you guys remember that? I hope. C and D. That's what translation form looked like in our previous unit. Well, vertex form, I mean, check it out. They're right next to each other on my little Desmo screen right now. Hopefully you can see that. They're the same. Just because vertex form calls it H and K and translation form calls it C and D, it's the same. Horizontal shift on the inside, vertical shift on the outside. Done. So vertex form of your quadratic is really helpful if you're wanting to know where the vertex of your parabola is. You look at that function, you're like, oh, okay, the a value is +1.5, so I know it's right side up. And then I can tell that it's in translation form, which means it goes to the left 1 and down 6. Your vertex is located to the left 1 and down 6. Okay, so those are the benefits of each and every one of those 3 forms. Standard form, the benefit is you know the vertical intercept without pretty much doing any math. Factored form, the benefit is that you know the x-intercepts with doing a minimal amount of math. And vertex form, the benefit is that you know the vertex by using the properties of transformation, translations, transformations, those are synonyms. So vertex form is helpful because you can transform the graph, aka move it left, right, up, down, and you'll know where the vertex goes if you're in vertex form. Okay, cool. I am now going to stop sharing my screen again. Stop.